A very warm welcome to all participants joining us for session 2 of TTDD 2025 titled AI Find a Central Role in 6G. I am Kanta Rathod, coordinator for this session. Before we begin, I would like to take a moment to acknowledge and thank our silver sponsor Tejas Networks. We truly appreciate their sponsorship and valuable presence in this edition of TTDD 2025. Here are a few hygiene announcements. All our online attendees will be kept on mute throughout the session by default. Kindly post your questions in the Q&A tab of the conference tool. This will be taken up during the Q&A section. Questions in the chat box will not be entertained. If you want to enlarge the presentation, please click on the expanding arrow icon at the top right of the presentation screen. The tool is configured for HD video. You may switch to LD in case you are facing any bandwidth problems. Attendees may like to visit the exhibit booth of TSTSI in between the sessions to know more about our work. Attendees can use the lounge facility for networking. The lounge will remain open till the end of the conference. The conference sessions are being recorded and will be posted to the TTDD website in the next few days. Now, I would like to introduce our session convener, Mr. Vishnuram Ovi, consultant at TSTSI. He has hands-on experience in the field of telecom industry for more than 27 years, developing and implementing standards and holds many international granted patents. He is an active member of National Working Group 13 in India and vice chair of ITUT Focus Group on Autonomous Network and co-convener of ITUT Correspondence Group on datasets. Welcome, Mr. Vishnuram. I now invite Mr. Vishnuram to take us through the session schedule and introduce our co-chairs. Sir, over to you now.
Very good. Thank you, Chandrakanta. Good evening, everybody. Let's look at the session details. Let's look at the next slide, please. Yeah. So today we are in session 2. Will AI find the central role in 6G? That is the title and theme. We have a very interesting set of keynotes. But before that, we have opening remarks from Abhijan from TCS. Then there are 3 keynotes arranged for today. The first one being Solving for Scale AI in 6G. That is from Jagan, is from Tejas Networks. Then there is the keynote 2 that is pre-recorded. Amit ji from GC Devotee, he will give that talk. And then there is Kannan from Altiostar Star who will give keynote 3. So each of these are the really interesting keynotes that we have curated for you today. Then there is a very rich panel discussion. There is that is titled Enablers for New Services and Applications in the Era of 6G and Generative AI, moderated by Rajaji from Tata Elxsi. We have good mix of colleagues here in the panelist, Anuradha from GE Healthcare, Gaurav from IIT Delhi, and Hemant from TCS. We'll have a Q&A session, and finally I'll come back for closing remarks. That is the brief overview of this session. We will go to the next slide. I will briefly introduce the session chairs. So you are in good hands today. Abhijan and Rajaji will co-chair this session. They are highly experienced as well as highly accomplished. Next slide, please. Okay, so you can see here, Abhijan is a senior scientist in Networks and Solution Services unit of TCS. He has 22 years of experience. He's vice chair not only in TSTSI SDSS Working Group 2, but also ITT Study Group 13. And he's representing TSTSI and India. He has authored RFC 7967, which is the first indigenous contribution from India to IETF standards, and there are several areas which I personally work with. Abhijan is a great colleague of mine. He has about 20 US patent grants as well. Then we have Rajaji, who is currently CTO of Communication and Technologies and Platforms in Tata Elxsi. He leads solutions for telco and automotive industries, softwareization, orchestration, digital twin, connected vehicles. These are all topics where we have had deep discussions with his team, as well as contributions. With over 25 years at Tata Elxsi, he has designed all these systems, RAN, scheduler, software stacks, etc. So yeah, I would think that we are in good hands today. Next slide, please. With this, I will call upon Abhijan to please open and say a few words, opening remarks. Over to you, Abhijan.
Thank you very much, Vishnuji, for the kind introduction. Thanks to TSDSI for giving me the opportunity to co-chair with my esteemed colleague Rajaji. To start this session, we have got an esteemed panels that Vishnuji has already mentioned. So just to start to kickstart the discussion and deliberations that is to follow on. So let me briefly put the overview of why we have this session and what we expect out of this session. So as XG ushers in a new era of unleashing possibilities for future applications with hyper experiences through reliable, real-time, resilient, and secure physical to digital continuum, it also challenges the limits of existing technologies. At the same time, a trend towards assimilation of the advancements in AI technologies into end-to-end networks and related use cases are emerging in every layer of the network, including application and services. This has led to the possibilities of using AI native networks or AI-ANN as an important exploration under the vision of IMT 2030, which so in our terms we can call it as 6G. At the same time, evolution of new AI techniques such as generative AI, reasoning models, and agentic frameworks have upended workflows in all spheres of technology. Global standardization bodies have already initiated streams of activities to define, study, analyze, and specify various aspects of AINN in the context of 6G or IMT 2030. In this regard, TSTSI has also started multiple study and work items on requirements, integration, and management of AI in future networks in a native manner. So, from TSTSI perspective, it is also intriguing to understand at this juncture the standardization gaps to be addressed and corresponding priorities in terms of value addition to end consumers, service providers, as well as network operators in the Indian ecosystem. Against this backdrop, this session dives deep into important issues such as would the advanced AI techniques bring quantifiable benefits while solving the challenges in 6G, such as management and operation of complex networks and services? It is also important to explore and prioritize the relevant standardization gaps. So there are two different complementing pathways, namely networks for AI, which is cross-domain data sharing, model transfer requirements, federated pipelines, and AI for networks, which includes domain or application-specific tuning of models, AI native architectures and applications. These two pathways need closer examination in respect to 6G networks as well as for applications and services. The session will study practical problems from use cases, datasets, models, and toolsets, research directions, and deployment models. The outcomes will include identify further areas of study in TSDSI and its global partners, pointing out specific opportunities for collaboration. So, with this background, let us quickly move into the deliberation session where we hear from our esteemed speakers. Our first speaker is Mr. Jagan Shantigram from Tejas Networks. Uh, so, if we have the introduction, Dr. Jagan Shantigram is a product development engineering leader, technology strategist, and responsible for outbound technology sales. He currently leads the network management and AI applications group at Tejas Networks. He has a BTech from IIT Madras, followed by a PhD from Columbia University, and has served as a CTO and as head of engineering in previous companies. Jagan holds 15 US patents in wireless and data networking. So, welcome, sir. Let's hear from you. So, over to you for the stage. Thank you.
Thank you very much, Abhijan. It's quite an honor to be in the midst of very illustrious industry experts. And thank you for the opportunity and the chance to speak on this topic. Um, Let me share my screen. Okay, please let me know if the screen is visible.
Yes, sir, we can see.
So I titled my presentation as Solving for Scale. The question on the panel is actually quite a relevant one, which is, are we going to see a very central role for AI in 6G? Um, just going by the speed of innovation that's happening in AI, it would be unwise to bet against anything in AI. So I think at least in my years of experience, I haven't seen any other technology after the internet itself, which is benefiting from so much of collaborative work and almost like a network viral effect. Of course, there have been many such types of technologies along the way, but AI is the speed at which it is evolving and innovating is mind-boggling. So I would not bet against AI for almost any application that can be imagined. But I wanted to sort of get to the bottom of uh, why 6G would be different, and how does it justify using AI in the 6G networking. And the question that presented, at least for me, was that we have to solve for scale. So I'm going to break my presentation in like two or three sort of broad categories. First, talk about what is different in 6G, what does scale mean in 6G, and then talk about how AI actually fits and broadly categorize it. All along the way, you can hold me guilty for oversimplifying things, but that is just the way that I try to understand the large problems. And if I misspeak technically on any particular topic because of the oversimplification, so please excuse me. Let me move forward. So I'm sure you have seen this circle of IMT 2030, and the key things that IMT 2030 defines in terms of what would constitute 6G. At a broad level, the key, the major points, at least significant. The peak user throughput, what in 5G would be like 20 Gbps is now 100 or 200 Gbps. The per user average throughput, what in 5G would have been like few hundred Mbps is now at least half a Gbps to 2 Gbps. The latency, which was acceptable as 1 to 10 milliseconds in 5G, is now targeted for sub 1 millisecond. the mobility of 1,000 kilometers per hour is like also double of what we were thinking in 5G. Essentially, this would allow us to point an antenna carrying the service over to airplanes as well, domestic airplanes, and maybe provide service there as well. The connection density, we have talked about this for a long time, where at one point we were thinking IoT is going to be the breaking application that will have like a lot of density on wireless networks. In 6G, it is a lot about sensors overall to include traffic from sensors and also bring them onto the network. So a minimum density of 1 million per square kilometers is sort of what is being asked for. So this diagram is also from ITU's recommendation for the different types of applications expected to work on 6G. But to qualify it or to paraphrase it in a slightly different way, there are a few things that stand out, that stood out at least to me. The first one is the data rates, of course, which you spoke about, which is 10x more than the previous, more than 5G. The other interesting thing in 6G is if we meet the 6G goals, then the complete network would turn into a computing infrastructure. What does that mean? So computing infrastructure is essentially a network of computers that are collaborating in a fast-paced way, where applications are talking to each other. So until now, we've been thinking about wireless networks as a communication infrastructure. What 6G, if it meets all the goals, will do is that it turns it into a computing infrastructure. This essentially means that we will be able to support on-device AI applications that have to sort of frequently synchronize data with collaborating peers, as well as centralized repository of data. The VR, AR, XR is a carryover from 5G. It's not yet quite achieved, but with the integrated sensing and communication, it is expected that extended reality will become an actual reality. The massive number of sensors and the data they collect, that will have to be processed with 6G. So besides the standardized type of applications which are expected, which is there on the right, these are some of the takeaways that I could think of that actually imposes certain expectations on 6G, which we'll try to kind of unwrap. So one curious question was, okay, we are expecting a 10x throughput from the RAN, but how is this throughput to be achieved? So when I went and looked at the bandwidth that is being considered, at least for early 6G deployment, so we are roughly looking at about 400 megahertz in around the 4.8 gigahertz frequency, and about 1 gigahertz in both the 7.1 and the 14 gigahertz range. Now, compared to 5G, that's about 2x to 4x. So in 5G, the peak bandwidth might have been about 100 megahertz, and here we're talking 400. We do not expect any significant change in the waveform in 6G. Of course, there will be certain multiplexing advantages when you go to much wider channels, as well as there will be optimizations that come through because of the use of AI and so on. but we expect roughly about 20 to 30% benefits from those kinds of advancements. And the third thing is there will be a higher MCS coding schemes for the constellation, maybe up to a 4K QAM. But this will also be under rare scenarios where the signal and the SNR and the link budgets, etc., can afford that kind of a dense QAM. So the key question in my mind was, okay, where is this 10x throughput going to come from? And it turns out that a majority of that is being targeted from what I see as geospatial multiplexing. So we are already familiar with the massive MIMO terminology and the technology which has been built for 5G. But with the higher frequencies, I'm sure most of the audience would know that with the higher frequency, your antenna wavelengths also inversely go down, which means that you can pack a very high density number of antennas in the antenna panel, which allows for many interesting ways to distribute bandwidth and power using beamforming. But there's also a potential for having distributed MIMO. There are research topics in considering cell-free MIMO or distributed MIMO, where within the same cell or parenting to the same base station, one can have many different radio elements, each of them radio antenna elements, each of them basically providing an independent rank to the user. So spatially distributed using beamforming and geographically distributed using distributed MIMO techniques. Now, each of these beams, each of these distributed antennas potentially provide a multiple to the available bandwidth. And this is basically one source of interesting problems where AI can actually play a significant role. So when we look at AI for 6G in a very sort of telescopic lens, we can think of the AI use cases as broken up into two broad categories. There's a centralized set of applications, which at this point of time, knowing what we know about AI, are somewhat obvious and a given. And every network equipment vendor and every network operator is already planning to utilize AI for a lot of these use cases. The key motivations for these, of course, are large volumes of data in the network. For example, a base station might have like 2,000 KPIs, which is pegging every 5 minutes or 10 minutes, which is getting recorded every 5-10 minutes. And all of that data is now going, and with 6G, of course, with the densification of the network, you have a much larger multiple of the data that has to be processed. Secondly, the operation of these networks, also because of densification and because of the number of devices on the network and the wider bandwidth, etc. These are very large networks and highly complex, and getting even more so. These become operationally quite expensive to manage, and it requires, if not a complete AI solution, at least AI assistance to be able to handle these. And thirdly, amongst the central category of applications, there's the efficiency of network resources and network optimizations problems that are not new to 6G, but probably just get more and more enhanced in terms of what is required. The second bucket as I see it, are basically the distributed applications. These are applications that get embedded in the RAN itself. And when I say embedded in the RAN, that includes the radio as well as the base stations, the CU and DU. So one can think of even applications that are based in the CU as centralized, but I choose to kind of put them all in one bucket as distributed in the RAN. Couple of opportunities there, include hardware acceleration, mostly because of newer ways of parallel processing and vector processing and handling teraflops of operations in like a single GPU, for example. And of course, the integrated data, which comes from the sensing that gets included. So tackling the easy one first, there's the centralized AI for the network. Broad categories, there are four types of AI applications. The first that I characterize as observation. Here, your network is collecting a whole lot of data that has to be made sense of, that has to be summarized, that has to be analyzed. And, it allows the network operator to efficiently manage the network. The second one is the forecast. So here we are talking about time series models, as well as using LLMs in some cases, but applying it to time series data, where we can essentially forecast what can come 3 hours, 24 hours, 7 days, or even 30 days ahead. There are many such models, and it primarily recognizes the fact that the network data has some kind of cyclic patterns. It could be a 24-hour pattern, it could be a weekly pattern. And even though this pattern can change, there are models that can sort of significantly capture the pattern in itself and give reasonably accurate forecasts. Basic models today can give accurate forecasts up to like 80% accuracy, which, depending on the applications, if we are doing, for example, anomaly detection, or if you're doing energy saving, might be sufficient. And when we aggregate data from multiple sources, there is also an increase in the accuracy because of the statistical multiplexing type of gains that you get when you combine data from multiple sources. The third category is the assist, where using natural language, primarily LLMs. And now we even have LLMs that are fine-tuned for telecom applications. It provides an easy human to machine interface where I can talk to my network using a natural language. I do not need that expertise and the knowledge of knowing the exact name of a particular KPI that I'm interested in. I can actually query the network with basic English language commands. And using Gen AI, my intent can actually be fulfilled. I can set, I can do complex configurations like, setting timer values for neighbor handoffs, etc. Just by, giving a command that I need an early handoff configuration for a particular group of cells, as an example. And then the final category is the agentic category, where we have agents, AI agents in the network that not just perform very defined rule-based functions, but they're also capable of doing having agency in the sense that they can take decisions and actions based on input data. And common applications for this are things like remediation. If there is something that goes wrong in the network, then the remedial action can actually be taken by the agent itself. Or it could be an assurance where a certain SLA is actually expected of the network, and the agent does everything necessary to make sure that the SLA is achieved. So going to the RAN, so today, the RAN today has many different complex algorithms, which in a broad sense, I would call them as closed form, in the sense that, given a set of input, these algorithms can actually be computed, and it gives you a particular output. And using the closed form understanding of the algorithm, one can actually understand exactly why we got that output. So if we look at all the different activity that needs to be performed in the RAN, this is sort of a well-recognized heuristic to identify what are the possible use cases in the RAN that might benefit from AI. So the very first criteria is that maybe a set of criteria is that there is a gap in understanding the system model, or knowing the system model as a closed form equation. For example, right? Let's say we are talking about channel state feedback in a TDD network. Now, one of the common simplifying approaches, is to use reciprocity. So look at the uplink signal coming in, and then use that to figure out what the downlink channel state looks like. Now, this is an approximation, and when we are dealing with multiple beams, as we will be in 6G, as well as multiple antennas and directionality from multiple paths, etc., this reciprocity principle might not be sophisticated enough to capture what the downlink channel looks like. So this I would put in maybe a category as system model shortcoming. Now, for everything that has a system model, what does the algorithm look like? Is it highly complex? And by complex, I mean, is it expensive to run this algorithm in the RAN? Now, a combination of these two, where either the system model is not very well understood or does not approximate the real physical phenomena, or a highly complex algorithm which has a very high cost of running in the RAN. For either of these types of use cases, the next question is the data available for AI? Because without the data, AI is kind of handicapped. The intelligence cannot really operate without the data. And if the data can be acquired for this particular use case, then it becomes a prime candidate for AI. There are a lot of references to this kind of heuristic, and it's fairly common. But I like it because it's reasonably simple and gives us a way to evaluate use cases in the RAN as to where we should try and focus our energies for building an AI model. So using, looking at what the industry is today looking at, there are few use cases that stood out for me, which I thought I'll share with you, which will be groundbreaking if we were to sort of successfully find implementations that make this work. The very first one is basically looking at essentially the very, the fundamental piece in the base station, and the UE, which is essentially taking data from, which is mapped out digital data, and mapping it into the constellation to symbols in the network. And then taking the same symbols that you receive from the channel, and then demapping it back into digital data. Now, this is if we are able to achieve this, then it allows us to scale very effectively in 6G. If you recall, in 6G, let's say we have 32 beams and we have, very high bandwidth. Let's say we have maybe 1500 PRBs overall. And that gets distributed into sub bands. Maybe there are 30 bands with 50 PRBs each. I'm just making up numbers. Then with then 30 bands with 32 beams, that gives approximately like 900 possible downlinks. And estimating the channel for each and every one of those can be a highly complex process. Plus, the 32 beams essentially means that we need to have 32 digital to RF chains, which can map digital data onto the symbols, which then get sent on the RF channel. So it is a scale problem, which is aggravated in 6G. And if you are able to do it using neural networks, both on the transmit as well as on the receiver side, then it can allow us to scale quite effectively using GPUs. The second problem, which is sort of well appreciated by most people working in this area, is essentially the channel state estimation. This also is a problem of scale, which scales up with the number of antennas multiplied by the PRBs that are available. And a fairly complex process to estimate the channel information, plus then to send that feedback back to the base station. So the channel state information is collected on the UE side, and then it gets sent back to the base station. So just the volume of this data being sent for every user device is quite enormous. And there are two significant techniques that are being investigated. One that uses predictability of some of this channel information to reduce the number of times the channel information has to be sent. And the second is to use AI techniques to compress the channel information, basically reducing the total amount of data that has to be sent.
Sorry to interrupt, sir. If you could please wrap up in just 1 minute, because we have a time check here.
Fair enough. I just have one more slide to go after this. There are a few others. There's beam management. There's positioning. Positioning is very critical to a lot of which is essentially location positioning for user devices. There are many use cases that depend on that. And of course, a lot of the sensor data, the volume of the sensor data, there are many different AI model techniques to manage the sensor data. So coming to the central question, will AI find a central role in 6G? There are a few opportunities here. Maybe the couple of things will be like hardware acceleration in the RAN, which allows us to sort of make existing algorithms much better. There's semantic communication, which is being researched, which allows us to compress data inside the RAN significantly. But we also, it's a mixed bag. We also get a certain amount of challenges that come with it. The first one is that the RAN is extremely sensitive to the total cost of ownership. So before we increase the cost of each network element, it needs to be sort of well justified with the benefit that we're going to get with the additional functionality. The second thing is something completely new for AI and comes purely for AI, which is that today the RAN is well explainable. So if we find a problem, we know what happened, and looking at the data, we'll be able to explain which algorithm did what. But with AI, this becomes somewhat of a black box, and it may not be possible for us to understand why the AI model made a decision that it did. Finally, the AI model might also lead to unanticipated output when it's presented with an input that is not seen, and it might cause something unexpected in the RAN. Not a major crisis by itself, but it is something that we have to keep in mind. Okay, that's all I have. I hope you got a good sense for how to look at the problem, if not the answer to the problem. Let me pause here. Let me know if you have any questions. Are we going to take questions in the end?
Thank you, sir. Thank you very much for this thoughtful deliberation, and you have very nicely and in a very lucid manner covered the different aspects, the risks, explainability, and the advantage that it can bring, and the ways forward. In the interest of time, we will take the question Q&A at the end of this session, at the end of of the talks. So please hold your questions for now. A request to the audience. Let us move to our next speaker. So our next speaker for keynote 2 is Mr. Amit Srivastava. Mr. Amit Srivastava is the DDG mobile communication, and he's also the vice chair of ITT FGINN, and represents Telecom Engineering Center (TEC). Mr. Amit Srivastava joined DOT as ITS officer of 1996 batch and has more than 26 years of experience in various fields of communications. He is presently heading the Mobile Technology Division as DTGMT in Telecom Engineering Center. He is chair of NWG 13 in TC, which studies and contributes for study group 13 of ITUT, and also chair of similar NWG for ORAN in DC. He's also vice chair of ITU Focus Group on Artificial Intelligence Native in Telecommunication Networks, in short FGAINN. So I think Mr. Srivastava is not physically present today because of some other responsibilities. He has to travel. We have a recorded message recorded speech of Mr. Srivastava. May I please request Chandrakanta Madam to share that with the audience?
Yeah, requesting host to kindly play the recorded video.
Good afternoon. My greetings to TSDSI, fellow eminent speakers, and all the participants. First, I would like to extend my sincere thanks to TSDSI for this opportunity to share insights in Tech Deep Dive Conference 2025 on a topic that is rapidly reshaping our digital future. Now, coming to the topic of the session, will AI find a central role in 6G? My opinion to this question would be yes, but let's go deeper. To understand AI's role in 6G, we first need to ask what exactly is 6G. The answer begins with the International Telecommunications Union. In June 2023, the ITU published recommendation ITU RM2160 that was titled Framework and Overall Objectives of the Future Development of IMT for 2030 and beyond. This document serves as our lighthouse, charting the vision for IMT 2030 or 6G. Among the 6 broad user scenarios outlined in this framework, one is especially transformative: AI and communication. This is not merely about using AI to assist the network, it's about embedding intelligence into the DNA of the communication system. It's about a future where AI does not simply run on top of the network, it runs through it. The envisioned use cases speak for themselves. We are looking at AI assisted automated mobility, collaborative robotics for medical and industrial purposes, distributed inference and learning operating seamlessly across the edge and core, and real-time digital twin that simulate and continuously optimize networks as they function. In this paradigm, AI is not just powering applications, it becomes an integral part of the network fabric. In fact, AI related capabilities have been elevated to the level of key performance indicators for 6G. These capabilities included distributed data processing, AI model execution, real time inference, and AI driven service orchestration. Even the other uses scenarios defined in the IMT 2030 vision, such as immersive experience, integrated sensing and communication, ultra reliable low latency communication, and ubiquitous connectivity all depend on AI as a core enabler. But to truly appreciate how far we have come, we need to look back also. In the era of 1G and 2G, networks were largely static. Intelligence, if you could call it that, was purely manual. Human operators configured and optimized network by hand. In 3G, we saw the rise of centralized network management systems. These brought a level of monitoring and automation, but they remained reactive and rule based. With 4G, we witnessed a significant leap, the advent of self organizing network or SON. These networks could self configure and self optimize, taking automated decisions based on predefined rules, of course. Then came 5G, and with it, exponential growth in network complexity and data volumes. SON alone could no longer handle the evolving demands. To address this, 3GPP introduced two vital functions: the Network Data Analytics Function or NWDAF, and later the Management Data Analytics Function or MDAF. These capabilities were designed to support the full life cycle of AI in the network: training, validation, deployment, inference, and retraining across multi-vendor, multi-domain environments. The result? A network that could observe, learn, and adapt without human intervention. And with 5G advanced, intelligence is no longer a bolt on, it's a core design feature. We now see AI embedded in the RAN for beamforming, channel state information prediction, and mobility optimization. In the core network, NWDAF leverages analytics for user experience prediction, slice assurance, and energy optimization. Furthermore, AI model management is becoming standardized, ensuring that AI systems in the network are trustworthy, auditable, and explainable. The point is, as the telecommunication network evolves into a flexible, cloud native implementation, AIML based network optimization becomes crucial. Current implementation of AIML in telecommunications face limitations, including siloed and fragmented deployment that hinder interoperability and holistic optimization. It also struggles with scalability due to high computational resources required and the challenges of managing vast amount of data. Integration into existing network operations is also complex and resource intensive, and maintaining AI model performance over time is also challenging. This limitation makes it hard to ensure optimal overall system performance, leading to the consideration of AI native methods. Now let's look ahead. In 6G, AI will not be a component, it will be a principle. We are envisioning AI native interfaces where machine learning algorithms help define modulation and coding schemes, that too in real time. We anticipate federated learning environments where models are updated across distributed nodes while preserving user privacy. We expect real time inference at the edge, eliminating the latency of centralized processing, and we see digital twins, virtual mirrors of the network, constantly learning, simulating, and optimizing the system. In essence, the network becomes intelligent not just in how it behaves, but in how it is built. It becomes self-learning, self-evolving, and self-scaling also. In upcoming 6G, it will not only AI for networks, but also networks for AI, and in fact, AI framework or AI layer. Therefore, in 6G, we must also consider how networks will be designed for AI. Of course, in 3GPP, now AI for 6G and 6G for AI both are being considered. In the future, AI will be everywhere, embedded in cities, vehicles, devices, and infrastructure. To support this intelligence, networks will need to offer ultra reliable, supporting very low latency communication. They will need seamless connectivity between learning agents. They must enable massive data offloading and distributed model training. In short, 6G network must become the computational and cognitive backbone of the AI driven world. You may also be aware of ITUT focus group on artificial intelligence native in telecommunication networks called FGAINN. This focus group is studying AI native approach and will be preparing a technical report after exploring and defining the fundamental changes needed in network architecture to fully harness the potential of AI. This focus group works to identify the requirements, challenges, and opportunities that AI native network will bring to the global communication landscape. It describes AI native as the pervasive use of AI and a required accompanying data infrastructure in all subcomponents of an entity rather than adding on an AI based component to an existing non AI based entity. It refers to the integration of inherent, trustworthy AI capabilities within a system's design, deployment, operation, and maintenance, making AI a fundamental aspect of its functionality. This approach utilizes a data driven and knowledge based ecosystem where data and knowledge are both consumed and generated to create new AI functionalities or to enhance and replace static rule based mechanism with adaptive learning AI as required. AI native optimization transforms the entire network structure into an AI framework, replacing more modules or even entire communication layers, and solves inefficiencies by enabling adaptive optimization and end to end training for a more autonomous and efficient network. In essence, AI native networks are designed to inherently understand and adapt to new use cases and trends, enabling more autonomous and user focused network experience. This is a shift from traditional network design where AI functionalities are added on top of the existing structure. The aim is to embed AI deeply into the network's architecture to drive innovation and efficiency in the network. Recently, India also hosted the meeting of ITUT Focus Group AINN meeting in June 2025 on 11th to 13th June. Along with that, a Built-a-thon event was also organized, and it was pleasant to see that good participation from academia with support of industry in the event to demonstrate the POC on AI network approach in telecommunications. TSDSI is also contributing in the use case work group on native AI support for dynamic distribution of inference tasks in an edge cloud continuum, and I would like to congratulate Shri Abhijan Bhattacharya also for his good work. In March 2023, the Government of India released the Bharat 6G Vision document, you all know, setting a bold agenda to design, develop, and deploy 6G technologies that guarantee intelligent, ubiquitous, and secure connectivity, elevating global living standards, and establishing India as a world leader in 6G by 2030. To drive this vision, the government has upped the stakes significantly, funding advanced test beds as well as to promote domestic R&D and support over 100 research proposals on 6G. Bharat 6G Alliance has already inked memorandum of understanding with global 6G alliances and hosted the inaugural International 6G Symposium at WTSA 2024 and India Mobile Congress 2024, demonstrating India's commitment to shaping global telecom futures. The 6G research in India is also focused on the use of AI in communication network. Recently, I participated in the TTDF symposium organized by Department of Telecommunication in IIT Madras campus. To give a background to the audience, The Telecom Technology Development Fund, that is TTDF, is a flagship scheme of DOT launched to boost indigenous R&D in next generation telecom technologies and bridge the digital divide in rural and remote areas. The scheme aims to promote technology ownership and indigenous manufacturing, create a culture of technology co-innovation, reduce imports, boost export opportunities, and creation of intellectual property. During the discussion held in the symposium, as I was part of the track one, which was discussing the projects related to AI and communication, semantic communication, I can say that it is really difficult now to separate AI from further research leading to 6G. That is, many of these projects are based on inclusion of artificial intelligence in physical layer, waveform design, beam management, sensing, secured communication, semantic communications, etc. 3GPP Release 20 stands as a crucial milestone in the evolution from 5G to 6G, acting as a strategic bridge between 5G advanced enhancements and the initiation of early 6G studies. While it continues to strengthen 5G advanced by refining technologies such as advanced mobility management and intelligent analytics in both the RAN and the core network, it also lays the groundwork for the future of mobile communication. Artificial intelligence, once seen as a support tool, is emerging as a central architectural pillar. Release 20 significantly expands AI's role from machine learning techniques used to predict radio link failures and optimize handovers to advanced network functions like NWDAF and MDAF that enable slice assurance, anomaly detection, and energy efficient operations. Beyond 5G, Release 20 launches essential 6G oriented studies exploring concepts such as AI native air interfaces, real time distributed learning, and semantic communications, where networks interpret and act upon meaning rather than just raw data. These developments set the foundation for a network that is not merely reactive but anticipatory, capable of self optimization, adoption, and cognition. With innovations like sensing as a service, federated learning, and digital twins also on the agenda, Release 20 is not just a continuation of 5G evolution, it is the springboard into a fully intelligent AI native 6G future. So now let's return to the original question, will AI be the central to 6G? 3GPP also started discussing about 6G for AI along with AI for 6G as I mentioned earlier. How much of AI will be there, time will tell. But as of now, it can be said that the answer is not just yes. Yes, it's already embedded in the global standards and architectural blueprints. But with the central role comes central responsibility. We must ensure that AI in 6G is trustworthy with decisions that can be explained and audited. It must be secure, protected from manipulation or misuse also. It must be efficient, supporting green, sustainable operations, and it must be fair, free from bias, and inclusive by design. The real challenge ahead of us is not simply embedding AI into the network, it's embedding AI responsibly, scalably, and ethically into a global, real time, mission critical infrastructure. In the coming decade, AI and 6G will not evolve separately, they will co evolve, tightly interwoven, mutually reinforcing, and that I believe is not just the future of communication, it's the future of cognition, of connection, and of civilization itself. Thank you once again to TSDSI and organizers of the Tech Deep Dive conference and to all of you for your attention, patient hearing, and engagement. Thank you so much.
So we thank Mr. Amit Srivastava, sir. It would have been really a great pleasure if we would have him here and have this session. So Mr. Amit Kumar Srivastava has nicely put the AI into the context of 6G and made us understand of what is the importance and how it is going to be intertwined, and at the same time how India is taking or gearing up for indigenous development, indigenous in both AI and 6G, how the policies are improving or adapting to strengthen our inner strength, and at the same time how India is playing its role to assume a leadership position in the future with AI intertwined with 6G. So we haven't received any questions for this session in the Q&A. Anyway, we are going to take all the questions at later. So moving to the next speaker. Our next speaker is Mr. Kannan Kadir Velu, Vice President, Engineering, Altiostar. At Altiostar, a Rakuten Symphony company, Kannan is at the forefront of deploying cutting-edge cloud-native LTE and NR Open RAN technologies. His leadership in engineering spans over few pivotal years, culminating in his current role as Vice President of Engineering, where he spearheads the software development, deployment, integration, and enhancement of 3GPP ORAN networks. So over to you, sir. The stage is yours.
First of all, thanks to TSDSI for inviting me to speak in this tech deep dive. And thanks for all the participants and the speakers. So we had two speakers speak about the AI's role in 6G. So some of my discussions are already, we have seen the same aspects of how AI is going to play a significant role in 6G. So I have pretty much similar content. So I'll try to skip where possible. So coming to this topic, so we know that AI is basically is a digital realm of reality, right? So we have a very close alignment of digital and physical world going on all around us, right? It's not just AI. It's been going on for a while, and this is part of the human evolution, right? So we have started with basic communication, and then we started data and things like that, and it's going towards. It's all part of our overall human evolution when you take a very big picture. Right?
Sorry to interrupt you, sir. We are not able to see your full screen presentation.
Okay. Is it better? I mean, now we are able to see?
Yes.
Okay. Yeah, so so as we were discussing, the merging of digital and physical world is happening for over a period of time, and that's part of our human evolution. And communication has been part of the central aspect of the human evolution, right? So the networks have also been catching up on the human evolution, and 4G or 5G or even 6G will be going towards that direction for the overall human evolution. So what we need to really see is how is AI really trying to fit into this scheme of things, right? That's what we want to uncover today. However, due to the time allotted, I'm still trying to keep at a very high level. So we need to start with the basics of what is our IMT 2030 vision, and what are the capabilities that are envisioned and what are the use cases, right? So the previous two speakers covered almost all the aspects of this. However, we'll just try to touch upon the wheel diagram and the palette diagram that we have from the ITUT. So if you see, the 5G had the triangular aspect which covers the EMBB with MMTC and URLLC, and that was part of the IMT 2020 vision, right? Now, IMT 2030 has expanded three more areas of integrated sensing and communication, AA and communication, and ubiquitous connectivity, right? So apart from this, there are four different aspects that IMT 2030 envisions, which is connecting the unconnected, right? Then another important aspect they are emphasizing is on sustainability and security and resilience and ubiquitous intelligence. These form the entire wheel diagram of IMT 2030. Now, turning our attention towards the new capabilities that IMT 2030 is adding as part of the what we call as the palette diagram, is expanding the IMT 2020 capabilities, as we can see in the lower quadrant in the green, right? So we had reliability aspects, latency, mobility, and a few aspects that are covered, right? Now, on top of that, there are some new capabilities that are being added by IMT 2030, where there is an emphasis on coverage. There is sensing related capabilities to be added. And as we discussed, sustainability is being added. And one of the things that we are talking about is AI, right? But the whole telecom network, or right, the whole communication network consists of major players, right? Different players, different components that are involved. So interoperability is a very key function that is needed for a new capability that is needed for IMT 2030, right? And then there are enhanced aspects such as positioning, whereas they're trying to narrow down to 1 to 10 centimeters, right? So we can see some of the applications when we go and discuss the use cases, right? So the same IMT 2030, when we try to see from a larger perspective of the human communication evolution, right? When we see 4G to 5G to 6G, there is a increase in everything, right? Latency reduction, whereas coverage focus is expanding from just urban and rural broadband communication towards ultra reliable low latency communication, and then it is going towards a global coverage using satellites, UAVs, etc. So the aspect is more, right? We are trying to cover more. So as Dr. Jagan covered, the scale is what is increasing from 4G to 5G to 6G. The peak speed is scale of the speed. The latency reduction is again the scale of reduction. So if you see all other cases, most probably we should look at the main use cases of 4G was restricted to mobile internet, video streaming, OTT, etc. Right? When we moved to 5G, we started looking at smart cities, AR, VR use cases, right? When we are looking at 6G, holographic communication is playing a centralized role. Along with digital twins, we are looking at metaverse and other concepts, right? So we are looking at multiple spheres of aspects that we want to improve towards achieving the IMT 2030 vision for 6G. The same thing, when we look at it just from the scale point of view, the last column that if you see, there is 10 to 100x scale difference between 5G and 6G, right? That's what we are targeting. Such a grand scale of things is humanly not possible, right? So the answer is obvious. We need automation. And what is that automation? It is not just that we do it once and then it's going to remain as it is, right? That's how we have been doing the automation. The industries, all these automations are, we do it once and it works the same way multiple times. But we need automation which dynamically changes, right? That is what is AI, right? So it has intelligence for the automation. So if you want to deploy something and then the conditions change, it should adapt and then it should continue to operate and provide the best services. This is exactly where we are going towards our vision that we have with respect to 6G. So what it comes down to is adaptability, right? That's basically what the 6G network has to offer. So I mean, in terms of what is adaptability and what are we talking about? So is it going to just talk about the peak data rate? It's going to adapt to the channel conditions of the UE. Are we talking about something else, right? So we are talking about the entire network. The network has to adapt to the changing conditions towards the UE or towards the network. For example, when there is congestion, there is scaling, right? The network has to scale to cater to the congestion or the high peak performance that is required peak period, right? So that's basically what AI is going to help us in different aspects of our network. So it's not just one aspect that we are trying to cover. So these are all IMT 2030 visions, right? So I think Dr. Jagan covered some aspects of how the RAN will realize these kind of aspects, right? So if we look at, there are two in the preface we saw, there are two pathways we can look at: AI for network and network for AI, right? These are the two aspects. However, I would like to see it as all inclusive, in the sense we need to start with AI for network and then prepare the network for AI as the second step, and then provide AI as a service for all subsystems that are part of the whole network. So what I mean by this is AI for network is, initially we are trying to optimize, make the network adapt to the changing conditions, right? So those are all certain use cases where we try to optimize the resources, energy efficiency, increase the energy efficiency, and adapt to the traffic scaling and things like that. So these are all already part of 5G, right? Now we need to create a network for AI. What is this talking about? This is basically, you need to create a platform, right? Your network has to support execution of models, and it has to cater to all the IMT 2030 capabilities or the vision that we saw, right? So it has to create a powerful platform to provide AI whatever it needs. For example, it needs to provide the data for the AI to work. It needs to provide the processing power the AI needs, and there has to be a low latency communication infrastructure that has to be part of the network. So this is the second stage. As part of 6G, we need to create the network for the AI, right? So we have been doing AI for network with 5G. Now we have to create the network for AI, and then we are well on our way to provide AI as a service. So as you can see, this is our third stage of our AI native blueprint or AI native narrative, I would say, right? So once we have created AI for network and network for AI, we go towards the AI as a service, where we provide AI functionality as a service, starting from intelligent robots to seamless immersive communication. We embed AI intelligence, right? Intelligence in every aspect of the end use cases. That's basically how we would like to incorporate AI into the 6G network in stages. So what are the foundational capabilities that we need to have towards AI native 6G, right? That's the next aspect we need to see. So we have summarized some of the aspects that we need to look at. One of them obviously is the AI native air interface. So the air interface, so as you know, we have a protocol stack that exists. I've just reused some of the publicly available diagrams. So when we discuss in the next stage, the protocol stack that we see here has to collapse to give the kind of speed that the network requires, right? However, this particular diagram is the AI native air interface. Basically talks about how the network is dynamically learning and adapting, right? So the RAN needs to dynamically learn and adapt. It has to focus on precise beamforming and then seamless connectivity by avoiding this aging channels, right? When the UE is mobile, we might be allocating. However, the UA has already moved, so there is delay introduced. So we would like to avoid that. The second aspect of the AI native 6G is network digital twin, as NDT, as we know, right? The most important aspects of the digital twin is to replicate in the virtual world the real world and use that as the sandbox, right? So create a sandbox. So why is creating a sandbox so important? Because we are talking about scale. The amount of devices that are going to communicate or connect in this 6G network is 100 times bigger than 5G, right? Larger than 5G. So we need to have an environment which can accommodate these things, and we cannot physically test all this, right? So we go into the digital world, create a sandbox environment using the digital twin, and then perform extensive scenario testing. So that's one. You can use the digital twin to do RF planning, and we can do RF optimization, the network optimization. All can be done in the digital twin and then implemented in real world, right? Then the third aspect we are looking at is federated learning. This is a very important aspect that we need to look into the 6G, where we need to spend a lot more aspects is with respect to privacy security, right? So and of course about the transport planning, the infrastructure planning, right? So if you maintain a centralized model, right, you need to send the data from each and every node towards the centralized model, and that's where the AI model will run, and it will then come with inferences, right? Whereas in a federated learning model, we are going to train and execute on the local devices. The data will be trained on the local devices. The inference will be sent to the centralized model. That will be published to all other models. So that's basically going to enhance your network. The execution speed will increase because you're not sending volumes and volumes of data towards a centralized server, whereas you're only sending the inferences, and the inferences now published back to all the models, and models are enhanced uh, uh, now and then, right? So that's basically what is happening. So the training is happening in the local data with the local data at the local device, whereas the model update is happening centrally, and that gets propagated to all other models which are in edge or core, right? The fourth aspect is ISAC, which is integrated sensing and communication. As we saw, massive machine type communication that we have seen in 5G is again increasing 100 folds. So each and every aspect or every device that we have are going to be connected to the 6G network, right? So for example, this is one important aspect of where AI comes into the picture. Envision car, right? The connected car that we have been talking in 5G. The connected car is going to sense something that is coming in front, and then it is going to take actions, right? Where 6G can come into the picture is it already knows there is another device that is, or a vehicle coming in front or in the wrong direction, and then adapt, dynamically inform the this vehicle that there is a blockage or we'll have to slow down, right? This is different from just sensing. Here we are applying the AI in the sensing by using the knowledge of another device present in the same physical location, right? So you can understand how AI is coming into the picture with respect to integrated sensing and communication. So we are talking about massive amount of devices. AI is able to interpret what's happening and then act coherently to manage everything on behalf of us, so that we can have very comfortable living, right? That's everything is towards that. We are also, I mean, everything is about human centric evolution, correct? The fifth aspect is evolving the air interface from a wave propagation perspective, where we are bringing reconfigurable intelligent surfaces, which basically helps with radio wave propagation. As you can see here, it is intelligent enough to enhance the radio signals. Thereby, it is increasing your network coverage and signal strength. And this will also help with the spectral efficiency, which is a goal in the IMT 2030 vision, right? So these are all our foundational capabilities that we are looking at from the 6G. So we started with the question on whether AI will play a central role in 6G. So we know what are the foundational blocks, foundational capabilities 6G should have to play a vital role in 6G development. So AI is, as both the speakers mentioned, right? AI is not an afterthought like 5G. AI is an integral fabric of your 6G network. So the scale at which 6G is envisioning itself to be, it is not possible without dynamically programmable network capability, which is only possible through AI. So the particular question is already answered, right? AI is a central fabric of the 6G network. It is there everywhere. It is an enabler of 6G rather than it's not a component, it's an enabler. Without AI, I don't think we can see a 6G network in reality, right? That's basically what we wanted to cover. Now we'll look at one aspect of the capability that we are hoping. How is 6G going to achieve a 0.1 millisecond network latency, right? Is this even reality? Correct. So the 5G network has promised 1 millisecond. This is 0.1 millisecond. So how is it possible? So there has to be a drastic change in the network, right? There has to be an architecture evolution. There has to be a AI network, AI native network where the data routing. So there has to be a breakout. The data cannot go to the core network. It has to break out from the edge towards the server, whichever, whether it is YouTube or a gaming network, it cannot go via the core network. So the whole network has to be broken down into edge. So you have to bring the core components of your user plane data path towards the edge, and that is the only way you can achieve. So there have been a lot of local breakout features that have evolved over a period of time. We had 4G having a local breakout for specific use cases, especially for example OTT. The OTT applications, right? They already have edge servers. For example, Netflix or YouTube, they have their own servers at the edge of every city. Correct? I mean, it cannot be centralized. So they have already moved. The applications are moved. The network has to facilitate. So it can only do that by breaking out without going towards the core network. So you need to now bring in the UPF towards the edge, and then you also need to bring the AI into this to do edge computing to learn about what is data path I should use for each and every use case or every user rather, right? The second thing we are looking at is high data rate, that is from terahertz of frequencies, and that's what we are that's how we are going to achieve, which is basically shorter wavelength. So there is going to be massive amount of radios that have to be deployed to achieve this scale, right? We already discussed about the data routing decisions that we have to take, and then the architecture evolution. The second thing is the protocol stack that we saw in the AI native interface, right? That architecture is not scalable, right? We, in fact, in 3G, we had RNC and then Node B. In 4G, we brought the RNC closer to the edge, which is the Node B, which we called as enhanced or evolved Node B, right? In 5G, we are trying to do a similar thing. However, with Open RAN, we have disaggregated the network into second level network versus millisecond level network, which is basically your DU and CU. DU is a real-time network, where a real-time device, whereas CU is non-real-time, right? Now, when you want to have a very high speed, low
Sir,
latency.
sorry to interrupt, sir. Could you please wrap up in next 30 seconds? We have a tough time check here.
Sure.
Thank you.
Yeah. So basically, what we need to do is collapse the network protocol, avoid retransmissions, and this is the direction where the 6G will go towards to create ultra fast signaling or data where we have to do protocol stack optimization. So that's basically how we will achieve 0.1 milliseconds. However, what we really need to understand is these are all for specific use cases, right? For a general use case, the propagation delay of is going to play a limiting factor to achieve this 0.1 millisecond, correct? So the main theme of this session was to talk about AI. We know that AI is going to be a central role in 6G. However, can we realize 6G? That is more important question. There are a lot of technical hurdles uh, that are going to be faced. First of all, how do I prepare my network for AI? Right? It's going to have high computational complexity and energy consumption. Number one problem. Second, how do I get data for computing, creating the models? Every operator have their own proprietary data, right? They don't share the data. That's another problem. So for example, the US market, the Asia Pacific market, the Europe market, or even the operators within each country do not share data across. So the data are existing in silos. So the quality data is not available. So the model is going to be as good as your data, right? Then the testing and validation of your whole network. Second, interoperability and standardization. As we discussed, interoperability is going to be a key aspect in the 6G realization. And then comes our bigger issue of ethical and societal implications, right? How is privacy and surveillance going to be taken care? How is the data that we have will inherently have bias that will get into your model, algorithmic bias and discrimination. And then there will be a digital divide because with the people able to access and not able to access, and AI exploitations, right? So the way to avoid, or rather to realize 6G, is to create an ethical and responsible standardized AI development and deployment, right? So for this, there has to be a global collaboration and cooperation for data sets, simulators. There has to be a common life cycle of tools, and the RAN and core network has to evolve to be a dynamically programmable network elements, network functions, right? So if they're not going to provide you dynamical programmability, just having AI sit next to it is not going to help you, right? AI has to be part of the RAN and core, and it should help you to dynamically program. That's when you have a close collaboration between uh, the AI and the RAN, AI for networks, right? And we need to have proper trust framework created, explainable AI. These are the solutions for what is the challenge that is ahead. So with this, I will leave you with a question that as a food for thought. So we have discussed about how AI is going to play a centralized role in 6G. Now the question is, will this pervasive AI native 6G be our greatest opportunity for global inclusion and human flourishing, or is it going to be our greatest challenge in maintaining control, privacy, and equity across our interconnected world? So the last point is something that we need to think about, right? We are trying to evolve, support this human evolution, the communication evolution. However, are we going to go towards our opportunity or towards a challenge? Thanks, TSD, for this opportunity. Thank you.
Thank you very much, sir, for this nice and very enriching deliberation. You have covered almost all the concerns, aspects, and the foundational aspects where we need to apply and think about AI in future, intertwined with 6G. In the interest of time, let us close this part of the of today's keynote part of today's session, and let us straightway go to the next part, which is the panel discussion. And all the questions, if there are any questions, you may please put in the Q&A section. Request to the audience, and we can take it at the end before closing the session, or we can have the experts answer them in the Q&A section itself. So may I please now call upon stage Rajaji, and to take for to move forward with the panel discussion. Over to you, sir. Thank you.
Thanks, Bijan, and thanks DSTSI and then Mr. Ram for providing this opportunity. And at this point of time, at the last session, it looks like it is very clearly established that AI is going to play a central role. And we take that assumption, and then from there, we discuss with distinguished speakers about the enablers for new services and application in the era of 6G and Gen AI. With me, Dr. Anuradha, Dr. Hemant, and Dr. Gaurav are here to discuss about the key enablers which are going to determine the new services and applications. Can we go to the next slide to introduce? So let me call upon Dr. Anuradha here. Anuradha had been heading as a Innovation and Technology Director for Healthcare for more than 2.5 decades. Had a very rich experience in research and development, product delivery, and managing interdiscipline missions, large missions. And she is currently heading the 5G interest group. And that's a very relevant topic because we are looking at the killer application. And one of the eminent speaker talked about for the 6G itself, AI is going to be the killer app. So we will draw upon Dr. Anuradha's experience in getting her views and opinions about it. The next panelist is Dr. Gaurav Ghatak. Dr. Gaurav Ghatak is a faculty member in Department of Electrical Engineering. He had been doing a pioneering research in the MAC and 5-layer algorithm for 5G and 6G communication, especially how they can be adapted from adaptive applications and then bring in machine learning algorithm. So we will try to listen from him and learn from him about how the adaptiveness of the AI can be brought in for leveraging the 6G network. And welcome Dr. Gaurav to this session. Then we have Dr. Hemant Kumar Rath. Dr. Hemant brings in a very rich experience working in TCS on applied research. And he has also continued to teach. And he had been having, again, 2.5 years experience, both on research and academy. So we have a very interesting blend of the panelists, one from product, technology and innovation, and from academia research, advancing the machine learning algorithm and the AI into the communication, wireless communication. And then Dr. Hemant on the applied research. So just before I hand over the podium to Dr. Anuradha, the quick observation what we have is in the 6G, it is from the beginning, it had been quite convincingly established AI is going to play a central role. However, one of the biggest, I would say, a pain point the industry is facing is on the monetization. It's how that in 5G, there was a comment about still there was a lot of gaps in how the 5G is monetized. So 6G is going to bring about even more bigger challenge when the monetization problem comes in. And there are enablers in terms of the edge, in terms of the data exchanges possible, in terms of the AI being from the internet, AI, the whole 6G network is going to be AI backbone and so on and so forth. But how in the respective industry vertical like healthcare and other spaces, the AI native application is going to make a bigger impact on the society as well as is trying to solve the monetization problem. I'll call upon Dr. Anuradha to share her experience, expertise, and viewpoints on this.
Thank you. Uh, Thank you, Rajaji, and thank you, TSDSI, for giving me this opportunity to share my viewpoints here. Uh, so, what I would like to do is to put in a perspective of use cases on what are the different kinds of use cases that can potentially leverage this 6G or communication technology to make lives better. And being in healthcare, I will talk upon a few of the healthcare uh, uh, examples or use cases. Now, a few years ago, when we talked about anything tele, so be it telemedicine, teleradiology, etc., etc., the whole reason why it started off was for improved access. So when you say improved access, it was for people in remote areas who didn't have access to doctors. Now, if you look at this whole notion of the iron triangle of healthcare, which is actually taken first introduced in a book called Medical Dilemmas: Infinite Needs versus Finite Resources, it describes three compelling health issues. One is access, quality, and cost. Now, we want to reduce the cost, we want to improve the access, and we need better quality. And somehow the whole communication technology has a great role to play in all three of these areas. So I will keep that theme in mind when I talk about some of the upcoming or existing use cases that are there. So if you look at what is already there, right? So we have tele ICU, we have telemedicine. So tele ICU is where you have there is there is a shortage of intensivists in the country, and so you actually cannot bring very ill people to Taiwan city. So you have an ICU in a remote village which is monitored using a camera or other equipment. You have wearables devices and all of it, and then anyone after a post operative care can be in a tele ICU and you can remotely manage them. And just to give you some numbers, it's a $5 billion market. Then you have a patient being monitored remotely via devices that are hooked onto them. It could be wearables, it could be other devices which are there. And now it is expanding to multiple diseases, and we will see a few examples on that. Then you have teleradiology, where you have a shortage of radiologists. So you have somebody in some other country who's actually writing your radiology reports. Then you have metaverse, and which could potentially, by augmenting virtual environments, help you with surgeries and all that. Then all of us know about robotic surgeries. Now people are actually talking about remote robotic surgery or telesurgery, and this has actually happened where even in India. So it probably happened a year back or year and a half back, I don't remember exactly. So India's first indigenous robotic system was used to perform two telesurgeries on patients within Gurgaon and Jaipur. And most recently in 2024, there was an experiment where, you know, uh, a robot actually uh, connected to the NASA and did an experiment of a surgery. Basically, it was not a surgery, but it kind of tried to lift up a rubber band to kind of prove that something is actually can be done remotely. So the entire robot was operated from the ground station, and the robot was up there and in space, and it could actually do something. Now, this actually gives a lot of opening into the healthcare space, where you're not only trying to improve the access, but you're also trying to improve the quality of care, because you're having access to better doctors and clinicians who are more experienced. Then there is also the concept of digital twin and precision medicine, where you're looking at to provide personalized care for an individual which needs a lot of data. So when you need a lot of data, there is when you want to do personalized care, there is genetic data, molecular information, your past records, your comorbidities, a bundle of things which needs a lot of bandwidth, and which essentially will improve the way in which you treat your people. But of course, again, bandwidth is an issue, and we hope that 6G can kind of solve that, 6G and 5G. If I, kind of talk a little bit more. Sir, how much time do I have? I'll give a few examples.
I think you can go for a few more minutes, ma'am.
Okay, for a few more minutes, right? So if you just look across the healthcare segments, right, where would communication actually help? One is in the whole clinical space and the therapy space, and other is in your asset tracking and maintenance of your services. Asset tracking and maintenance is slightly a different field, basically because just as clinicians are important to solve your problems and provide diagnostics, machines are equally important. You actually don't want your machine to have an unscheduled downtime when you have multiple patients waiting in for a scan. So it is always important to do predictive maintenance or predict the failure of these machines, ahead of the curve. So for which again you need a lot of data to kind of build your models and run your models. Now the challenge there is these machines are actually deployed in hospitals. The hospital network has a plethora of devices connected. They could be all the big iron machines which generate a lot of images, heavy in bandwidth. It could be multiple bedside monitoring devices which are completely, they have low latency and heavy what do you call data rate, uh, time series data that is coming out, and on top of that you have this local wi-fi and other stuff that is going on, and then you have your machine data to be sent across. Now machine data is also very important. You have multiple machines, there are multiple sensors. From the machines data has to flow, but when today in the current scenario, when you prioritize, the machine data is prioritized last because they always want to send the patient data in advance. Now that is a huge space where the network slicing and others can play a role. Then there is all the asset tracking. Assets are moving across devices and are moving across in a hospital environment or outside a hospital environment. Again, that's one great use case to work on. Now that talks about the machines, but when you come back to the treatment and therapy and diagnostics, we are talking about monitoring sensors, which are real-time IoT monitoring sensors, which could monitor anything starting from a sleep to a cognitive disorder for elderly people. There is also a talk about trying to remotely monitor people with dementia, people in pain based on their movement, and prevent falls in advance and all of it. Then you have a remote care. Then you have wearables. Now wearables could be anything starting from your watch, your ring, and other stuff to all the kinds of patches that we have today, including CGMs. Everything is continuously pumping in data. Then you have remote surgery that is coming in. So remote surgery is not just viewing, it is also a two-way communication between the doctor and the patient, and you require a lot of precision. You need speed, and you need reliability of the network. Then of course we talked about imaging, and then we are also talking about diagnostic systems. Now therapy is another thing that is coming in quickly, where you also need to have a lot of stuff around the technology around therapy. Let me try to see if I can get an example on therapy, right? So if there is a way to kind of you know so today you see people who have insulin pumps, and these insulin pumps are kind of more operated manually. So there is a timer, and then the timer tells you based on your measurement of your sugar levels that your insulin needs to be pumped. Imagine if that can be done remotely by your doctor or your caregiver. So those are some of the examples of care and therapy and diagnosis and imaging and all of it. And definitely everything needs data, and data needs bandwidth to move from one place to another to where the processing end is. Because of course you cannot have your compute at the endpoint or location or in multiple places. So with that, I hand it over back to Rajaji to take it on with the next panelist.
Yeah, thanks, Dr. Anuradha, for giving us some use cases which covers both on the
I think
we get
Rajaji's
use cases like
connection is
necessarily
not.
going to the body control and then in care. Now on Dr. Hemant to talk about necessity networks.
Want me to speak?
Dr. Hemant, yes. Can you discuss about how the network slice and
Okay.
possibly digital twin can bring in,
Lil-
in management and orchestration of network to provide an application awareness?
Thank you, sir. Yeah.
Yeah.
So I think most of the speakers have already pointed out very interesting points. See, before getting into this application awareness, let me talk about the three things 6G is talking. One is AI native. The two other things actually we are all missing is green native and cloud native. So while we talk about AI native, so both green and cloud also has to be very much considered here. Then when you talk about these 6G applications and 6G network, because 6G network has to be placed, a network is the horizontal for all kind of verticals. Now when the network is in place and your applications are running, say maybe for healthcare applications or say telematics applications or any other applications like your other vertical applications can also there, retail applications. All applications require some kind of KPI, right? They have some extremely low latency, like say some millisecond kind of delay and extremely high throughput, terabits per second kind of rate. And then also need, there are a lot, I think someone has to, Radhaji sir, can you, yeah. So these are the basic KPIs, like say rate, delay, and then reliability is another aspects. Then coverage and capacity also are the other things. So these are the KPIs you have to ensure from the applications to run in a seamless manner. Now the network, which is the 6G network or 5G network, we have 5G net, 4G, 5G network today, and going forward beyond 2030 or so, we'll be having 6G kind of network. So the network has to be application aware. That means applications requirements have to be understood and the network has to be orchestrated in a very seamless manner. That means if the applications require say 1 millisecond or some 1 millisecond delay, then there has to be like a provisioning of the network. The slice has to be created if the slicing mechanism is there or whatever things is there. That has, because this is not only one network, there will be like hybrid network, heterogeneous network components will be there, and so many different vendors will be there. So all the people, all the network devices, network elements, network technologies has to be configured in such a manner such that the applications are running they can run very smoothly. Okay, that is the application awareness. For this, what you need to do, the autonomous network requirements are like sense, analyze, decide, and respond. So you need to sense the network requirement from the applications. Then accordingly you analyze how much network has to be there, okay, and what is the requirement, and then you decide like whether you need multiple slices or you need this much of rate or you need to have this much spectrum. Okay, this particular band has to be aligned. Those things has to be that is part of respond or execution mechanism. Now while doing all the things, because you have to understand the applications and take care of all the things, while doing all the things you need to like find out these things, and these before executing or before responding, you have to test it out in a digital twin forum, because you cannot go to directly to the network and implement it. That may create certain kind of problem. That is the reason you need to have a full place digital twin where all these things has to be deployed, tested, tried and tested, and that has to be real time. Most of the things has to be tested, tried in real time, and then has to be deployed or executed in practice. Like, and while applications are there, suppose applications suddenly require more bandwidth, more throughput, okay, then that has to then, or the applications are facing some problems, and your entire system or the agents are there, AI agents or certain things are there. They found out that there are some issues, and that those issues have to be solved. And for that, you need to create one more slice and add it, or you need to add extra bandwidth. So they are the solutions. Those solutions have to be provided by GenAI or have to be provided by classical AI. That is the reason when you talk about green, you have to decide whether you need to go for GenAI or you have to go for classical AI mechanism. That's what you have to find it out, because your latency, your throughput has to be very, very specific. Very, very, very tight requirements are there. That is the reason you need to have a digital twin. And digital twin, that means you find out a problem, get a solution from the AI or the classical AI from the or the Gen AI, put into the all the solutions into the digital twin, go back and see what performance you are getting. If that is fine, then you implement, execute or respond it. Otherwise, again you try it out. That means the loop will continue till you get the best thing, and that has to be in real time. And that is the major major issue is going to be faced in actual network design, network orchestration framework. That's a very interesting point we have to see from the digital twin perspective and application aware. Not only application aware, the network aware applications. Sometimes here we have LD, like a SD bandwidth or HD video, right? So if the network is not good, can the applications automatically get switched to different different kind of modes? So that is also has to be there from the network perspective in 6G or AI perspective. So AI has to be not only in the network, the AI also has to be integrated in the application domain. That is also one interesting thing I think we have to think over it when you talk about the network and the digital twin. Yeah. Thank you, sir.
Yeah, thanks, Hemant. I think you brought about energy balancing with energy usage, and then how the application awareness can be brought in the network by sensing, analyzing, and using the digital twin as a test simulator, and have a balance of usage of AI versus Gen AI. Now I draw upon Dr. Gaurav to comment how in the MAC-PHY cross-layer optimization, these kind of application awareness and the AI and Gen AI can be leveraged. Maybe Dr. Gaurav, you can comment on it.
Thank you. Good evening again. It's a pleasure to be a part of this panel. I have been listening to the talks quite intently. Actually, the first keynote speech by Dr. Jagan covered most of like the good stuff that I wanted to discuss anyway. Specifically, the parts of the 6G network which can find applications of AI in particular. So what are the characteristics of a problem that we are looking at, where adaptations of MAC and PHY algorithms to take into account AI algorithms will find use, right? So I mean, regarding this question today, whether will AI play a central role in 6G, we must begin by recognizing a bit of our legacy, right? So wireless communications in general have been built on very rigorous mathematical foundations, decades of work starting with the work of Shannon. So many of the procedures which are in MAC and PHY layers, like modulation, coding, channel estimation, are highly optimized through closed form models, some form of convex optimization, so that you know for a guarantee that these are your optimal solutions. And currently they are so heavily optimized, they are also lightweight. It's not as if there is a huge complexity in implementing these algorithms. So as most people would estimate that the goal of AI is not to replace these well-engineered mechanisms, with black box AI models which are data driven, but augment these traditional approaches. And 3 or 4 particular cases where AI would augment these existing mechanisms are first, where models are inaccurate or incomplete, where real-time adaptation is computationally infeasible, or maybe the system complexity is so much that it defies any analytic modeling. So maybe to come back to your question, I'll maybe give a few examples in terms of the MAC and Phi architecture, where how it can make a change, right? So the MAC and Phi layers are classically they rely on these strong models. For instance, AWGN channels, Rayleigh fading, queuing models, Poisson arrivals, exponential service times, etc. Which all of them, they enable efficient optimization and derivation of good insights for system design. But real world environments realistically are complex because of multipath dynamics, hardware impairments, and non-stationary behavior, and so on and so forth. So AI and ML can come in as tools for modeling and emulation of these complex environments for decision support. So for example, ML can learn from observed data where accurate channel or interference models are unavailable. So it can also be a solution which is AI driven for link adaptation, where non-ergodic channel observations are there. Generative AI in particular can also have applications in simulating edge cases, hard to model environments. I'll give an example which was already covered, that of semantic communications, for example. So in essence, we are looking at hybrid architectures where you have theory driven modules which are well understood mathematically and are heavily optimized, and then there are data driven modules which can handle this complexity and uncertainty, and they go hand in hand in some synergistic manner to deliver these claims that 6G is putting forth, right? And that's what something which I'm also interested to look at. From a use case perspective, of course, new use cases have come in, but I mean, to be honest, as a mobile user, my problems have still remained over the past decade. I don't have good indoor connectivity. What does a mobile user want? Wants good connectivity inside. I still have call drops inside. I want some kind of connectivity on the move. Although there have been enough activities in standardization as well as technology development, but also in trends in India, in cars in India, I don't have connectivity. There is a huge densification, and its energy implications are still under question. I mean, there are good energy management solutions which are being investigated, but how all of these things will come together to meet the claims is something which has to be looked at. To come back to this generative AI in particular, one example is from semantic communications, which Dr. Jagan also touched on. It's a paradigm of moving from transporting bits from the transceiver to receiver to moving information, right? So it's comes under the umbrella of goal-oriented communication. So as long as you are able to make the receiver act in a way that it was supposed to act, whether it's a medical device, a wearable, or a industrial robot in a warehouse, or a factory floor, etc. It doesn't really matter if you are not able to effectively communicate the bits as you intended to, as long as the meaning is communicated. So this comes under the task-oriented communication. You need task-oriented encoders. You want to infer from latent intents. You want to generate semantically equivalent messages. For example, if there is a missing message at the receiver, you would want to generate it locally so that the intent is kept the same, even though the bits were corrupted, or high bit error rate was observed. So an example can be generative model can summarize and transmit only the essential features or generate responses at the communication side. There are other examples. For example, for AI to be meaningfully support this MAC and Phi adaptation, it needs rich real-time observability. So it means going beyond the classical metrics of throughput and SNR to include channel sparsity statistics, interference patterns, feedback delays, unreliability, so on and so forth. So here it's a kind of a gray area to add on to the 2 points of unexplainability and unpredictability, which Dr. Jagan had pointed out. I would like to add on untransferability. So you take example of the reconfigurable intelligent surfaces. Right? You train with enough amount of data inside a office setup, and you have optimal parameters for a particular scenario. These are not transferable to a different room of the same office. These are not transferable even if you come in with a blockage and add it to the situation. You need to have retraining of the entire stuff again. And the crux of it is because they are not mathematically tractable. Why they are resulting in some solutions as they are predicting. So these are challenges, of course, which remain in Mac and Phi, and hence there must be a good synergy. I want to reinforce this point that there must be a good synergy of mathematically robust existing communication models along with this data-driven optimization on the fly using Gen AI and classical AI, so to say, to augment their performance. Whether this means that AI is playing a central role in 6G? Yes, maybe, but not by discarding communication theory, but acting as a companion to communication theory. For example, by emulating the environment where models break down, by learning to interpolate when data is scarce or uncertain or cannot be transmitted at all, or there is high errors, and enabling adaptation at time scales which are unimplementable by classical algorithms. So you again take the example of a distributed MIMO, which was presented, right? So you need real-time information of all the users' channels to all the transmit antenna elements in real time connected, so that you have joint beamforming in near real time. If it's a telesurgery application, for example, you would need the need high degree of reliability, and hence you deploy this distributed user-centric MIMO system. But they must be exchanging information at such an unimaginable rate about channel state informations that it's simply cannot be feasible with current processing without such AI solutions. So this human-centric hybrid intelligence combining the domain knowledge of telecom with machine learning is, I think, the way to go forward. And I, for one, would look forward to how they are successful enough to meet the goals that are laid in front of us in this 6G roadmap, the wheel diagram that we saw.
Yeah, thanks, Gaurav. And we'd like to thank Dr. Jagan also to point out the possibility of a very robust mathematical model combined with a data-driven empirical model, how it can possibly improve the overall system efficiency, and possibly the channel effects can be compensated, channel estimation can be better, and maybe with the federated learning and some kind of model rollback into the CI/CD kind of architecture into the RAN, there could be a potential for further amplifying the benefits what we are discussing. So with this, possibly we can throw open to the Q&A session to the panelists. Chandra, if there are any questions, we can pose it to the panelists.
Yes, sir. So there is a question from Mr. Pankaj. How integration of AI in 6G can effectively aid in elderly care and reduce the mortality due to sudden heart attacks? Yes.
Yeah,
Okay,
it
I
naturally
will.
goes to Dr. Anuradha. Yes. Thank you.
I will try to answer this question. Okay, so there is a use case. There is a hypothesis that we can aid in elderly care to reduce the mortality because you can diagnose early by having, for example, continuous monitoring or by with data from you. So basically, having monitoring devices, or even by having a remote cameras to identify if the patient is undergoing discomfort. Now, so that is what we think will help in identifying this, that this patient is is undergoing some discomfort and there is a chance of having a heart attack. But then the actionable I aspect of it is to actually rush them to the hospital or whatever. So it might give you a few indications of the symptoms, is what is the most practical answer that I can give you at this point in time.
There is another question from Ms. Pratha. Are there instances of tactile internet being used in robotics surgery in India as of now?
So there is always haptic feedback that is provided in robotic surgery, but I am not sure of the tactile internet being used.
It is being used in UK, that we have seen, but in India, we don't have a full-fledged 5G network where this robotic, the tactile things have been deployed fully. But there are research going on to actually do these things. Maybe very soon you will be able to see that part.
Right. So in India, the current robotic surgery happens in a hospital, in a room. It is not across like a 5G network. It's not remote yet. We have seen one example of it being remote, but that is not scaled yet, is what I would say. But quite possible that the technology will come.
Okay. Thanks, Dr. Anuradha. If there are any other questions, can take it up.
Yes, sir. So one more question from Ms. Pratha. AI interfacing time may contradict the low latency objective. Does it mean we should restrict to those use cases where low latency is not priority?
I think that's what why you pointed out. Because when you talk about latency and when you talk about AI may take more time. So you may have to use instead of GenAI, maybe classical AI you have to use, so that real time you'll be able to find it out. So that is the balance you have to have it to have AI or GenAI, and the classical AI has to be, whatever the classical AI has to be trained properly so that your latency part is appropriately maintained.
And the next question is from Mr. Jagan. Any thoughts on how integration of sensing can improve communication?
Okay, I think a lot of work has started, in fact, both in integrated sensing and communication as well as in the RIS part. From RIS perspective, if I say, it is going to improve both capacity and coverage significantly. And I think we have also done a lot of work from TCS Research. My team have already done some work. And with the combination of integrated sensing and communications, I think the both capacity and coverage can be significantly improved, because you, as Gaurav was mentioning, that you have to reaching that certain capacity. So you have to have certain mechanism to have your capacity improved significantly. Maybe Professor Gaurav can add to it. I think a lot of scope is there.
Yeah, indeed. So, in my opinion, it's not just sensing improving communications, but both improving each other. So, sensing is no longer for finding out the location and positioning, right? So, it's also to enable some location oriented services. So, you think about indoor gaming kind of networks. So, you have not only localize the devices, but also maybe enable location informed beamforming in quick time, right? So, and on the other hand, for more and more precise localization or sensing, you would need the communication to be more effective. So if you have distributed sensing, now having fusion of all this distributed sensing information, communicating to each other in real time, so as to enhance the location services. That's, I think, the other way around, how communication can enhance the sensing as well. An example is V2X networks also, where individual vehicles have very limited local sensing capabilities with their radars and cameras being obstructed, especially in Indian scenarios. On the other hand, the network has a more global situational awareness because of the number of devices connected to it, and maybe in future, if there are more and more V2X connected cars, then you have individual location information and situational awareness information fused together in the network and communicated, dissipated for real-time control, let's say. So it's, to me, it appears like if sensing and communication are integrated, it's like 1 + 1 is not 2. It's something which is more than 2, with each of them synergistically improving the other one. And of course, integrating them in a common hardware, like you do in RIS, as Dr. Hemant mentioned, is of course a part of it. I think the other panelists can add to it, but I think it's integration not only on one device but across the internet, where each can improve each other.
Thank you, sir. And thank you to all our esteemed keynotes and panelists for such an engaging discussion. I now invite our session co-chairs, Mr. Rajaji, to share the concluding remarks and formally close the session. Before we conclude, a gentle reminder to all attendees to share your feedback using the feedback link. I am posting it in the chat box.
Thank you, all the speakers. It was a wonderful learning for every one of us, I guess. And especially the AI is more or less established. It's going to play a central and vital role. And we all going to contribute towards how it can provide inclusivity and sustainability. I think that is the challenge what we need to look forward to. And again, thanks DSDSI and Tejas Networks for being a sponsor and being an active contributor to this also. And thanks every one of you, and have a great evening. Thank you.
Thank you once again for your active participation. We hope you enjoy the remaining sessions of TTDD 2025. Details of tomorrow's session are available in the chat box.